Yeah, thank you. I must thank the organizers, especially Madam and Pradeep sir, for giving me this opportunity to speak to all the students on the radiological parameters as a part of this hybrid course on water quality. So, as suggested yesterday or day before yesterday, I think we can be interactive in between or through some video. I have inserted two videos in the PowerPoints as well. And the students also can stop me and ask any question in between, or at the end also you can take questions. Okay. So before I move on to the radiological standards and parameters for the water quality, let us first have some idea in first two, three slides about the radioactivity because normally, generally, the students or the public may not be so much acquainted with the radioactivity concepts. So radioactivity is a decay process by which an unstable atomic nucleus loses its energy by radiation. And when it was first discovered by Rontgen, then Becquerel, and then pioneering work of Madame Curie and Pierre Curie, a lot of radioisotopes have been discovered and their properties have been studied. So mainly the two ways this nucleus they lose their energy if they are unstable. One is the fission, nuclear fission, and another is the nuclear fusion. In the nuclear fission, a larger atomic nucleus split into two or more smaller number of nucleus, and in that process it loses its extra energy, and this is a phenomena where mass to energy conversion as per the Einstein equation E equal to mc square takes place. So mass defect is basically converted into energy. So there is another phenomena which is fusion, which people are still working to make the fusion happen in the earth artificially. For that, we make two or more lighter atoms join together and form a larger one, and the extra energy is liberated here also. And this liberated energy can be in terms of the particle emission, or it can be in terms of the photon emission. When we talk about the particle emission, it can be the beta minus, beta plus emissions, that is the electrons or positrons, or it can be alpha emission, or in case of it can be neutron, which is a neutral particle, or in case of photon emission, it is mostly gamma ray and X-rays or different energies. Now, if you look at the periodic table, what I have shown here, you can see the all the sky blue color elements are having at least one isotope which is not radioactive. It means they have at least one stable radioisotope, one stable isotope rather. Now there are few green marked elements which are having isotopes which are very high half-life. It means they are almost stable in the geological scale. Their half-life is in billions of or millions of years. Then we have yellow and the orange one, where half-life is in the range of few years to even few thousand years. Then the red one are highly radioactive elements, and most stable isotope has half-life between several minutes to maximum of 1 day. Now the purple one you can see at the end of the periodic table after 1008 atomic number. The elements they are very highly unstable and their half-life is very short. So this is all about the different elements and their isotopes, which one is stable, which one is not. So based on this emission of the radiation from these isotopes, we apply the radioactivity for various applications. First one and foremost one, it is the power production, that is the nuclear energy, converting it to the thermal energy and converting it to the electricity basically. So that is the mostly most applied application of this nuclear energy. And second one is the various industrial processes where we use radiation to do some scanning, some neutron radiography, and all those things. Then in the biology, we use this radiation for the radiation induced mutagenesis or the different creation of the different varieties of fruit crops where will have the improved properties. Then the naturally occurring radioisotopes like carbon 14, then lead 210, polonium 210, they are used as a marker of the for the dating, means age of different substances or or matter we can find out by studying the radioactive decay of those naturally occurring radioisotopes. Then radiation has a huge application in the medical field. It can be in the diagnosis, it can be in the therapy for the cancer therapy and various chronic diseases. Radiation therapy is used, and in the PETs and SPECT scan, CT scan, and everywhere this radiation is used. Then we use it for the biological research, chemistry research, physics research, like an interdisciplinary research for neutron scattering and all. And of course, we have the application, important application of radioactivity in the national security as well. So now this radioactivity, how it is present in the environment? It is omnipresent in the environment, not only from the man-made sources. It is natural. Naturally, there are the total radioactivity which is present in this earth. 84% is coming from the natural sources of radioactivity, and only 16% is from the artificial sources. Now, among the natural sources of the radioactivity, the main one is from the cosmic rays, then soil, rocks, our food item, even our bodies, plants, all have some radioactive sources. They may mostly originate from the decay series of the different uranium 235 and uranium 238 isotopes, as well as from the thorium 232 isotopes. So the decay chain of these isotopes are having various, we call them daughter products. Those are radioactives, and they are always present in the environment. So, and radon and thoron, please remember, these two are two gaseous product in this change. No other daughter products are gaseous. So radon and thoron are the gaseous products in this chain. So they are going to have uh, uh, a high impact into the dose calculation or into the presence of this radioactivity in our day-to-day activities. So now in this table, you can see some of the naturally occurring radionuclides and some of the important man-made radionuclides. So with this, let us see a brief video on the introduction of the radiation.
When we hear the word radiation, it's tempting to picture huge explosions and frightening mutations. But that's not the full story. Radiation also applies to rainbows and a doctor examining an X-ray. So what is radiation really, and how much should we worry about its effects? The answer begins with understanding that the word radiation describes two very different scientific phenomena: electromagnetic radiation and nuclear radiation. Electromagnetic radiation is pure energy consisting of interacting electrical and magnetic waves oscillating through space. As these waves oscillate faster, they scale up in energy. At the lower end of the spectrum, there's radio, infrared, and visible light. At the higher end are ultraviolet, X-ray, and gamma rays. Modern society is shaped by sending and detecting electromagnetic radiation. We might download an email to our phone via radio waves to open an image of an X-ray print, which we can see because our screen emits visible light. Nuclear radiation, on the other hand, originates in the atomic nucleus, where protons repel each other due to their mutually positive charges. A phenomenon known as the strong nuclear force struggles to overcome this repulsion and keep the nucleus intact. However, some combinations of protons and neutrons, known as isotopes, remain unstable or radioactive. They will randomly eject matter and/or energy known as nuclear radiation to achieve greater stability. Nuclear radiation comes from natural sources like radon, a gas which seeps up from the ground. We also refine naturally occurring radioactive ores to fuel nuclear power plants. Even bananas contain trace amounts of a radioactive potassium isotope. So if we live in a world of radiation, how can we escape its dangerous effects? To start, Not all radiation is hazardous. Radiation becomes risky when it rips atoms' electrons away upon impact, a process that can damage DNA. This is known as ionizing radiation, because an atom that has lost or gained electrons is called an ion. All nuclear radiation is ionizing, while only the highest energy electromagnetic radiation is. That includes gamma rays, X-rays, and the high energy end of ultraviolet. That's why, as an extra precaution during X-rays, doctors shield body parts they don't need to examine, and why beachgoers use sunscreen. In comparison, cell phones and microwaves operate at the lower end of the spectrum, so there is no risk of ionizing radiation from their use. The biggest health risk occurs when lots of ionizing radiation hits us in a short time period, also known as an acute exposure. Acute exposures overwhelm the body's natural ability to repair the damage. This can trigger cancers, cellular dysfunction, and potentially even death. Fortunately, acute exposures are rare, but we are exposed daily to lower levels of ionizing radiation from both natural and man-made sources. Scientists have a harder time quantifying these risks. Your body often repairs damage from small amounts of ionizing radiation, and if it can't, the results of damage may not manifest for a decade or more. One way scientists compare ionizing radiation exposure is a unit called the sievert. An acute exposure to 1 sievert will probably cause nausea within hours, and 4 sieverts could be fatal. However, our normal daily exposures are far lower. The average person receives 6.2 millisieverts of radiation from all sources annually, around a third due to radon. At only 5 microsieverts each, you'd need to get more than 1,200 dental X-rays to rack up your annual dosage. And remember that banana? If you could absorb all the banana's radiation, you'd need around 170 a day to hit your annual dosage. We live in a world of radiation. However, much of that radiation is non-ionizing. For the remainder that is ionizing, our exposures are usually low, and choices like getting your home tested for radon and wearing sunscreen can help reduce the associated health risks. Marie Curie, one of the early radiation pioneers, summed up the challenge as follows: "Nothing in life is to be feared. It is only to be understood. Now is the time to understand more so that we may fear less."
Yeah, I hope the concept of radioactivity and the unnecessary fear surrounding it will not be in your mind after looking at this video. Now, let us continue to coming to the different standards of drinking water related to radioactivity. Who sets the standards? So, there are different organizations. First one is the World Health Organization, which sets the norms and the standards related to health and promoting and monitoring their implementation. So they only set norms and the standard. Now there are ICRP, which advise for the member of the public for protection in case of nuclear detonation, not in case of the normal time. And there is IAEA, International Atomic Energy Agency, which basically radiation set the radiation related policies, and it is the standard setting organization. And there is another organization under United Nations which is called Food and Agriculture Organization of the United Nations, uh, with a joint secretariat of this IAEA, WHO, and FAO. The standards on drinking water or food item on radiation are set basically. Then there are various national bodies which look at the standard and they decide whether the standard has to be followed or there should be some modification based on the geological scenario, political scenario, and demographic scenario in that particular region. So, like for us in India, we have Central Pollution Control Board, which gives the limits for various toxic elements as well as radiation related standard. And Bureau of Indian Standard gives us the standards for different analysis and all. What happened? Is it visible? Okay, I'll continue. I think in between my screen got off.
Yes,
So,
sir. It's
uh,
visible. Please proceed.
okay. In case of, and then we have Atomic Energy Regulatory Board, which basically gives the guidelines related to the radiation in different materials. Then in the US, they have Environmental Protection Agency, which takes care of all these things. Now, moving to the standards, there are two basic standards: the drinking water standards by the WHO, which gives the guidelines from drinking water quality, and it is an authority basis for the setting of the national regulations and standards for water safety in support of the public health. Then there are radiation standards which are formulated by various organizations. This is International Basic Safety Standards, which establishes fundamental safety principles, requirements, and measures to control the radiation exposure of the people and release the radioactive material to the environment. So these are the two latest versions. So what is the importance of this radiological standard? They are important because if we want to have a good health, we want to high standard of safety, and if we want to meet the sustainable development goal set by the United Nations in 2015, out of 17 sustainable goal, if you carefully look, many of them will need this this radiological standard either to be followed or for the analysis purpose. Anyway, so moving to the before moving to the radiation standards and the permitted limit of radiation in the drinking water. What is the basis of this radiological limit in the drinking water? The basis is the radiation dose. So we have to understand what is the radiation dose. As I told, there are various kind of radiation, either in terms of particulate emission or in terms of photon emission, but they have different penetration power. Like you can see in the first left, this image, the alpha is having the least. Even a piece of paper can stop the alpha, the least penetration power. Then beta penetration power is slightly more than the alpha, and X-ray is even more, and gamma ray can penetrate many things, and neutron is having the maximum penetrative power out of this particles or the photon radiations. So based on their penetration power and the amount of ionization they can cause in the tissues, in the matter where they are interacting, the dose will depend. So this another table shows the annual effective dose from natural sources at various locations on the earth. It is not uniform everywhere. Like if we talk about India, in the beaches of the Kerala, the natural radiation dose is quite high compared to the our national average or the world average value. The world average value of the natural dose from the natural radiation is 2.4 millisievert. I'll come to those things, what is sievert, millisievert, these things. So let us see the units of the radioactivity and radiation dose. From this, I'll be giving the definition of the doses as well, so you'll understand it clearly. So the radioactivity units, most of you know, it is becquerel or curie. 1 curie is 3.7 into 10 to the power 10 becquerel. So 1 becquerel is basically 1 disintegration per second. It means the one atomic nucleus disintegrate in 1 second. Then it is 1 dps, 1 becquerel, equivalent to 1 becquerel. Now it is the emission by this radiation gives the emission by the radionuclide. Now what is the absorbed dose? Absorbed dose unit is given by Gray. Gray is 1 joule per kg. 1 Gray is equivalent to 1 joule per kg. It will deposit energy equivalent to 1 joule in 1 kg of the material, 1 kg of the mass. Then it is called 1 Gray. Now, there are different types of radiation, and I told the amount of energy they are going to deposit in certain matter. It depends on the type of the radiation. So there is a term we call radiation weighting factor, WR. You can see in the top table. So alpha, X-ray, beta particle, this is less. For proton, it is high. For alpha particle and heavy ions, it is rather very high. For neutron also, it is high because they are going to deposit more and more energy into our body system. If we talk about the human tissues and human bodies. So when once we multiply this radiation weighting factor with the absorbed dose, that is in gray, we get the equivalent dose. The unit of this dose is sievert or millisievert in terms of sievert. Now there is another factor which we have to take into account. The different parts of our body, when we are talking about the human body, different parts of our body doesn't interact equally with the incident radiation. So different parts of our body are differently susceptible to the radiation induced effect. So we have defined a tissue weighting factor as well. Like you can see in the bone marrow, this gonad, bladder, and bone surface, and other tissues, the radiation tissue weighting factor is given here. So once we multiply again this equivalent dose with the tissue weighting factor, we get effective dose. So effective dose is the ultimate dose which basically a public or a radiation worker gets. So we when radiation dose or radiation dose limit we talk about this effective dose. So for public, the as per the standards or limit, it is allowed to be given 1 millisievert per year additional dose apart from the natural radiation dose. Due to the natural radiation, although it depends from the place to place, the world average value is 2.4 millisievert per year. So over and above of this 2.4 millisievert per year, 1% of general public is allowed to have 1 millisievert additional dose in a year. Now, for a radiation worker like me, the radiation dose limit is 20 millisievert per year, and deterministic dose is 1 sievert. Means at 1 sievert dose, you will see deterministic health effect. Okay, so and this is again shows the distribution of the doses from different sources, and take much time on this. It, as I told, it comes from the cosmic ray, terrestrial gamma radiation. This gamma radiation basically originate from the daughter products of the uranium and the thorium decay series. These are the external kind of exposure, means we are getting the source is outside. Then there is external exposure, means the radiation source is outside and it is giving the radiation from outside of our body towards our body. Then there can be internal exposure. Internal exposure means the source, the radiation source, radionuclides is inside our body. It is mainly through the radon. I told radon or thoron, these two are the basically gaseous products and it is present in the atmosphere. So when we inhale this, it gives us certain doses, as well as we have certain food items or drinking water where suppose potassium, all of you know, potassium we have to consume every day. That is an essential element. The potassium is having a certain concentration of potassium 40 that is naturally occurring. So K40 is having gamma radiation. It gives gamma radiation dose. So every day we are consuming potassium in terms of salt, in terms of other food products. So that is also giving radiation. So total radiation dose we get from all these sources is 2.4 millisievert, although it is having a wide range in the from place to place. Now, from where this radiation can enter the human body, it can be through different routes. First, it can be through the absorption or adsorption through our skin or through our eyes. It can be through ingestion through our mouth if we have it in terms of the food items or as a drinking water. Then it can be injection through the skin or other areas through the cut portion of our body or through injection. Then it can be inhalation through our lungs, right, as I told. For the radon, it is through a inhalation to our lungs. So these are the major four routes through which the radiation can go inside the human body. Now, let us again see one video, then we'll dive into the further details of the radiation standards and limits. Okay, so let us start the video.
Radiation with enough energy to cause changes at the atomic level is called ionizing radiation. It can damage cells, so it's important to measure its potential health effects. But how? Units measuring ionizing radiation are commonly named after leading physicists in the field. The unit for radioactivity, for example, was initially named after Marie and Pierre Curie, pioneers of radiology. Scientists now use becquerel, Gray, and sievert as standard units to quantify radiation and estimate its impact on people. Let's take an example. Suppose Alex is standing close to a radiation source. The source emits radiation through decay or loss of energy of its unstable atoms. This radioactivity is measured in a unit called becquerel. Becquerel describes the number of atom decays over time. When Alex stands too close to a source of ionizing radiation, his body absorbs a dose of energy. This dose is measured in grays. Grays describe the energy Alex's body has absorbed, divided by his weight. But grays don't give a full picture of the effects of radiation. Some types do more damage than others. Certain body tissues are more or less sensitive to ionizing radiation. To calculate potential health effects, we use a unit called sievert. Sieverts take into account the type of radiation, the tissues exposed, and how much energy they could have absorbed. The bigger the sievert, the higher the potential health risk for Alex. Since 1 sievert is a large quantity, radiation doses are usually expressed in fractions of sieverts. A person's exposure due to all natural sources of radiation, for example, is on average around 2.4 millisieverts a year.
Okay, let us continue again. Now coming to the drinking water part, how the radioactivity come into the drinking water. So there are radioactive constituents of the drinking water. It can come from the naturally occurring radioactive species, as I told, like uranium, radium, etc., from the decay chain, basically of uranium and thorium. Then, because of various technological processes, like which involve the mining and milling of these radioisotopes, radioactive elements, the fertilizer industry. So from there, it can come into the aquatic system. And then there are manufactured radionuclides like we produce in our nuclear reactor, and we discharge them from the nuclear fuel facility, although it is a very controlled discharge, or in case of any unwanted discharge, or the radionuclides, whatever we are using as a nuclear medicine for the pharmaceutical as a radio pharmaceutical. So in case they come into the contact of the drinking water, they may pose a risk of the drinking water contamination. Then manufactured radionuclides also can be from the waste side, and because of the nuclear fallout, although now there has not been many tests of nuclear explosion. There have been past releases into the environment because of this nuclear fallout, which also contribute to the presence of radioactive substances in the drinking water. So worldwide per capita effective dose, if we see from the diagnostic medical examination, average is 0.4 millisievert per year. As we undergo X-ray, CT scan, PET scan, SPECT scan, all these contribute to radiation doses, and sometimes significantly higher than our even annual limits. The nuclear power production contribute very less. The nuclear weapon testing even earlier, although I am talking about the earlier weapon testing, this contribute even more than the nuclear power production nowadays. And Chernobyl accident, of course, has some signature on this, on the contribution of the radiation into the drinking water system. So here I saw various natural radiation sources and human or man-made radiation sources. The contribution of drinking water to the total exposure, that is out of 1 millisievert, is typically very small. So Radionuclides from the nuclear fuel cycle and from medical and from other uses are limited by regulatory control of the source. So we need not to be worried about the radiation coming from this nuclear fuel cycle from medical uses because they are already limited by the regulatory control at the source. So basically, that radiation level, what we are talking about into the drinking water system, we are talking about the radiation from the natural sources, and the exposure due to this is typically very small. So, if we look at the radiological risk perspective from this point of view, radiological hazard, as I told, may derive from ionizing radiation emitted by the presence of radioactive substances in the drinking water. The risk is mainly due to the radon in drinking water derived from groundwater, and this dose is typically very low compared to that of the inhaled radon. So, more amount of radiation we get from the inhalation of the radon compared to the radon presence in the groundwater system. So this is the major dose coming from the inhaled radon, and even but this radon is important because it signature of radon may indicate the deposit. Deposit, I mean deposit of the radionuclides into the region. But radiological risks are normally very small compared to the risks from the microorganism and the chemicals that may be present into the water. So radiological risks are very small compared to the those risks. And except in extreme circumstances, the radiation dose resulting from the ingestion of the radionuclides in drinking water is much lower than that received from the other sources. The screening and the guidance level, which now I will be talking about, apply to the routine operational condition. They do not apply to the water supply contaminated during an emergency situation because of the radiation releases or explosion. The guidance and generic action levels for the emergency conditions are available elsewhere. So, to understand the level of radiation allowed into the drinking water, we'll have to see the reference dose level. The recommended reference dose level of the committed effective dose is equal to zero point 0.1 millisievert from 1 year's consumption of the drinking water. So it means out of 1 millisievert of the dose which is allowed for a public, zero point 0.1 millisievert can come from the consumption of the drinking water. And the graph you can see which shows the no observed adverse effect level, which is very low at even 10, and then lowest observed adverse effect level around 15 to 20, then LD50 value it comes, the percentage response where 50% are affected at that dose. Anyway, so this zero point 0.1 millisievert is very important. This will derive the concentration of the radionuclides allowed into the drinking water system, and it is, as you know, 10% of the total dose allowed for the population, and it has been recommended by both ICRP and IAEA, and these are accepted by most of the member states of the WHO, European Commission, and FAO of United Nations as well. Now, how this zero point 0.1 millisievert is derived, as it has been accepted by all mostly. This is comes from the nominal probability coefficient for radiation-induced stochastic health effect, which is in the order of 10 to the power minus 2 per millisievert. Multiplying this by a radiation dose level of zero point 0.1 millisievert annual exposure via drinking water gives an estimated upper bound lifetime risk of stochastic health effect of 10 to the power minus 4. It means 1 out of 10,000. The reference risk estimate for radionuclides is this is quite reliable due to the extensive scientific database that have included human population exposure data as well, and the background radiation exposure vary widely across the earth, but the average is 2.4 millisievert per year, and highest is even 10 times than this, means 24 millisievert per year. So 0.1 millisievert is not going to cause any significant health effect. Now, there are those coefficient of each radionuclides. This is for the adult member of the public, which is given in terms of the millisievert per becquerel. It means how much dose these radionuclides, different radionuclides, deposit to our body. So based on these parameters, we define the guidance level for the radionuclides into drinking water. Now the guidance levels is given by individual equal to individual dose criteria divided by the dose coefficient for ingestion of by the adult, as well as divided by the annual ingested volume of the drinking water, which is taken as typically 730 liter per year. This guidance level is meant for the individual radionuclides. The total zero point 0.1 millisievert allowed dose limit from the drinking water is for considering all the radionuclides together, but guidance level is given for individual radionuclides. Now, the how this guidance level comes into picture and why they are important, we'll see. The higher age dependence dose coefficient calculators for children do not lead to significantly higher doses due to the lower mean volume of the drinking water consumed by the infant or the children. See, one is in the numerator, another is in the denominator. So the RDL or these guidance levels are age independent. It is considered as age independent. These are the values easily available. The guidance level values from derived from all the radionuclides, all the common radionuclides which we encounter, which may encounter into the aquatic medium. So values are readily available. Now the limits of the radiation set based on these doses by the WHO and the Bureau of Indian Standard, I have given here. For the WHO, the dose limits is simplified as zero point 0.5 becquerel per liter for the gross alpha activity. Gross alpha activity means all the radionuclides, whatever is present or whatever may be present in the drinking water system, the total dose given by all the alpha emitted by those radionuclides, if it is zero point 0.5 becquerel per liter or less than that, the water is drinkable. For the gross, similarly for the gross beta activity, it is measured as 1 becquerel per liter. If it is for all taking consideration of the all the beta emitting radionuclides that are present in the water system, if the dose, if the level is less than 1 becquerel per liter, then the water is drinkable. For uranium, it is not derived by its alpha or gamma activity. It is rather derived from its chemical toxicity, because chemical it is more toxic than its radiological toxicity. So for uranium, the based on the chemical toxicity, its limit is only 15 ppb. Now, this is the WHO limit. If the water satisfies these two criteria, we need not to take any action. The water can be consumed from the radiological point of view. Now, there are Indian standard like IS 10500 2012 is the latest version, which gives us the drinking water specification. And similarly, the standards are available for packaged drinking water and packaged natural mineral water. And for the radioactivity, the Indian standards or Indian limits are given as for alpha zero point 0.1 becquerel per liter, and for beta, all the beta emitting radionuclides together, it is 1 becquerel per liter. Now, mm, this is kind of screening, you can say. First, we see the water, whether it contains alpha more than 0.1 or zero point 0.5 becquerel per liter, or and beta more than 1 becquerel per liter. If the water satisfies these two criteria, means the values are below the expected level, these levels, then water is drinkable. This is called screening. We are not basically measuring the actual concentration of the radionuclides into the water system. We are screening the total dose or total radiation from the water medium, because in most situations the radioactivity concentration in drinking water are very low, and detailed analysis of the radionuclides is not normally justified for routine monitoring, because in some setting radionuclides analysis might be resource intensive, and it is normally very costly, involve lot of instruments and all, and thus screening is a spectral approach, and these values are given based on the screening levels. So screening levels is one thing, and suppose it exceeds the screening level, then we'll have to go to the guidance level of that of particular radionuclide. So, and again, these screening levels and the guidance levels are conservative, and they should not be interpreted as a mandatory limit. Exceeding a guidance level should be taken as an indication that drinking water is unsafe. Now, what way has to be followed for checking the quality of this drinking water in terms of radiological parameters. I have told if we look at the WHO limits, we'll look for the gross alpha and gross beta activity. If the gross alpha activity is less than 0.5 becquerel per liter and gross beta is less than 1 becquerel per liter, simply the water is suitable to drink from radiological point of view because it is giving dose of less than zero point 0.1 millisievert, which we told the reference dose level. Now, if it is more than alpha is more than zero point 0.5 becquerel per liter or beta is more than 1 becquerel per liter or any one or both exceed this limit, then we'll have to determine the individual radionuclide concentration and we'll have to compare them with their guidance level. Guidance level chart I have shown if you remember. So that we'll have to compare, we have to individually determine the radionuclide concentration, we'll have to compare it with their guidance level and then we'll have to, from that guidance level, we have to take the dose. If there are 5 radionuclides present, all the doses we'll have to consider. And altogether, if the dose is less than zero point 0.1 millisievert for the alpha and for the uh, beta, it is sorry, this dose is not for alpha beta. This is together. All the doses, total dose, dose given by all the radionuclides together, if it is less than zero point 0.1 millisievert, then we can consider the water as drinkable. Okay, but if it is more than zero point 0.1 millisievert, then further remedial action is required to be taken to reduce the dose level and water is as such is not drinkable. The below formula shows the how to measure the activity and how to consider all the guidance levels of different radionuclides. It is basically a summation of the ratio of the concentration and the guidance level of a particular radionuclides. It should be less than 1. Now, this zero point 0.1, zero point 0.5 or 1 becquerel per liter and then if that is exceeded comparing it with the guidance level and if the dose from the considering all the guidance levels for all the radionuclides present there, if the dose is less than zero point 0.1 millisievert, then we can consider it as safe. That is for the normal situation. But in the emergency situation, the limits are quite high or the limits are not that rigid. So this is basically as there is very little choice in drinking water and it is sensitive in the public perception. Or providing alternate sources can be logistically very difficult under an emergency situation, particularly for cities and for a long period of time. So if a decision has to be taken that do not drink order has to be issued, then we need to have a clear basis for withdrawal of that order. Must not, and it must not undermine the confidence in the available water supply, particularly where limited or no alternate is available. Now, limit for the emergency situation, if we have to give certain limit, the generic dose criteria is 10 millisievert in the first year after the emergency. The screening values are therefore very conservative as activity will reduce rapidly. This 10 millisievert ensure the dose from all exposure pathway will not exceed 100 millisievert generic criteria. And if I compare this 10 millisievert per annum from all food, it is equivalent to 2000 becquerel per liter of cesium 137 and zero point 0.1 millisievert per annum for an adult dose of drinking water is equivalent to only 10 becquerel per liter. So you can consider how much conservative is the reference dose for the normal situation. Anyway, I'm not going into the details of the emergency situation. There are some procedures of the sampling. This sampling for a water reservoir or water resource has to be done at least once to determine their suitability for the drinking water supply before its design and construction. And once measurement indicate that it is in the normal range, the sampling frequency can be reduced. And if the source has the potential radionuclide contamination exists nearby, sampling should be more frequent and the reservoir has to be planned properly, may have to be abandoned or relocated. Now, how to measure this activity? I told the screening level is based on the gross alpha and gross beta activity. The gross alpha and gross beta activity we measure for that ISO 9697 for the gross beta and ISO 9696 for the gross alpha standards are available. One has to simply follow the standard to measure the gross alpha and gross beta activity into the drinking water. For the measuring radon, there are different processes. Sometimes you have to pretreat the samples, like you have to dry if it is solid sample, homogenize radionuclides. You'll have to separate, like through precipitation, extraction through resin, solvent extraction, and combustion of carbon 14. Now, the activity, apart from the gross alpha and gross beta activity, they are measured by different detectors. If you want to do the spectroscopy, means if you want to measure the uh, exact concentration of an individual radionuclide, we need to do spectroscopy, right? So, for that we have alpha and gamma spectrometry. I will not go into the details of these things. So if you are interested, we can discuss anytime. So normally the detectors used for gamma spectrometry are sodium iodide thallium detector, that is a scintillation based detector, or high purity germanium detector, which is a semiconductor based detector, which can give the individual concentration of each radionuclides, because the gamma energy emitted by the radionuclides is specific. And alpha spectrometry is done using PIPS detector or scintillator detector. Then liquid scintillation is basically used for carbon 14 and the tritium activity measurement. Tritium also is another important man-made radionuclides. If we don't measure the alpha, beta, or gamma directly, the smart spectrometry like ICP-MS, TIMS can be utilized for measurement of the concentration of different radionuclides. And then for neutron, although neutron I have not spoken much, and we use different proportional counter, boron line counters, boron BF3 field gas chambers and tube, because basically neutron is neutral, no, so it is difficult to measure by any detector. So what is done, so some nuclear reaction takes place inside the detector. So boron, it basically converts to lithium and it forms a alpha. It emits a alpha. That alpha then again ionizes the gas in the present in the gas chamber, the proportional counter, or it forms some kind of scintillation if we couple it with a scintillator detector. Anyway, so those are a different field altogether. So now coming to the worldwide values of this radioactivity in the drinking water, it is size specific, and in selected location it is not available many times. Even if some reports are available, there is non-uniformity in the report. There have been various standards, various parameters have not been optimized. So worldwide mapping of this radiation limit into the drinking water still is a dream, but people's water data, this initiative can be a very good uh, towards that, fulfilling that dream. We will have a better understanding or better mapping of the water quality data. And in case the radiation is, this is just for general understanding, I want to share one or two slides. That's in case the radiation is present more than the acceptable limit, we follow the ALARA principle. ALARA is as low as reasonably achievable. So different processes we may have to follow. We have to treat the water, and the QA, quality assurance, quality control, for any analysis like any other chemical analysis also has to be followed for the radionuclide analysis. These are for some additional readings, the references you may go through. And these are the QR code. I think it is connected to it will take you to the some questions based on this lecture. So let us answer those questions and let us interact. For the other questions also, I am available to answer. And thank you.
Dr. Basu, can you go back to the QR code?
Okay.
I request students to stay back for the Q&A session with Dr. Basu. We have a few questions here. Okay, we have students already. Bear with me. Okay, the first question is, which essential element is also present as radioactive isotope naturally? We have potassium as the, okay, there are other takers on calcium, sodium, and iron. Worldwide annual average effective dose from background radiation is? So Dr. Basu, we have most of them paying attention in class.
Are you showing those questions on the screen to them?
Yes. Aren't you seeing those questions?
Yeah,
Right.
the results I can see, yes.
Yeah. So the previous question they had all answered as potassium.
Potassium, yeah, 54 are
Natural
correct answer. Yes, yes,
yes.
yes, yes,
And the
yes.
next one?
This is also 2.4 millisievert is the correct answer. This is the world average value.
Right. Allowed annual dose from drinking water consumption under normal situation is?
If somebody are
I don't think they are. Okay.
okay, then I think most of the answers are received. But
Yes.
here I am little worried actually why most of the people have answered the wrong one. That this is zero point 0.1 millisievert. No, we are talking about the dose that 0.1 millisievert is allowed from the drinking water. It is not 0.01 millisievert. Because most of the people have answered that 0.01. I don't know how the confusion has
I
arisen, but
thought the less is better or safer.
sorry.
They probably thought the lower is safer.
Okay, okay, maybe. This I told towards the lecture, maybe they are not that much attentive. Anyway, so this is, you please remember for the students who are still online, that first is the screening approach. Screening is we see the total alpha and total beta activity. If it is less than 0.5 becquerel per liter for alpha and less than 1 becquerel per liter for beta, as per the WHO guidelines, it is drinking water is safe, because with that limit we are never going to reach this zero point 0.1 millisievert. Now 1 millisievert is allowed dose limit for the general public. Now out of 1 millisievert only 10% is allotted for the drinking water. You think that way. So that is zero point 0.1 millisievert, and other 0.9 millisievert is for all other routes like inhalation of radiation, ingestion of the various food items, potassium and all. Okay, so out of this, and then if we exceed that limit, we have to consider the concentration of individual radionuclides. And if we see the individual radionuclides concentration there, how at what concentration they are present, that concentration can give us what is the dose based on their guidance level values, what is the dose they are giving. So from that dose, we'll have to derive what is the total dose coming for the for that particular water sample. If it is more than 0.1 millisievert per year, then we cannot drink that water. So it is the uh, dose limit for the drinking water. But screening approach is follows, because you need not to do so much of experimental work, because identifying and analyzing individual radionuclides is really a tedious job. So to avoid that, the screening approach is followed. Once that screening approach is not satisfied, then only we have to go for this kind of analysis.
Yes, Dr. Basu. And I see we have a lot of questions online as well. I will
Okay.
share those questions with you. For want of time, I'm ending the class now because students have
Okay.
to go to the next class after this. I would like, on behalf of the students and online participants, I would like to place my gratitude for having you here, spending your time with the students. and for such a detailed and beautiful lecture. Thank you, Dr. Basu.
Okay, thank you, thank you. And these questions I'll be happy to answer through email.
Yes, I will share these questions with you
Okay,
and then I'll share it with the students.
okay,
Thank you so
okay,
much,
okay,
Dr.
okay,
Basu.
thank you.
Do we have any question in class? Just
Okay, I am
okay,
still on.
they are due for a next class, so I will hang up.
Okay, 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 okay.
Yeah. Thank you, sir. Thank you so much.
Okay, thank you, thank you.